Thanks.
Seeing as how it's about 5 minutes after 10, we'll go ahead and get started. I want to welcome everybody to the public food safety meeting for the California Regional Water Quality Control Board and our panel of experts that are with us here in the room. Welcome those folks that are on the phone. I don't think we'll do so much of introduction of everybody, since it looks like most everybody in the room are repeat attendees. So hopefully everybody pretty much knows everybody by now. And if not, you're welcome to come up when we take a break and ask questions, or if there's anybody on the phone that has any questions about who's in the room or whatever, we can answer those questions also. Couple introductory things. If you have questions and you're watching the webcast, you can email your questions to us. What's that email address, Rebecca or Josh?
It's waterboard food safety at waterboards.ca.gov.
So if you send an email to that with your question, staff will bring your questions up for the expert panel or any of the speakers. And we'll be happy to take questions by that method. Is there anything else you want to add, Dale or Josh or Rebecca?
None here.
One second. I guess we're having some issues on the webcast. Let me talk to Gene real quick. It's not being broadcasted.
Okay, I apologize for some of that. Also, I'll let everybody know that we've normally put stuff up on the web page related to these meetings ahead of time. We have a little bit of an issue with doing that because we have to make sure that all of the documents are compliant with the American with Disabilities Act, so that they are accessible to everybody if we put them up on our web page. So like today's presentations, we've not been able to put them up on the web page from GSI because we haven't gotten them certified as of yet that they are ADA compliant. We're hopeful that eventually that will end up on the web page, but for anybody in the room or anybody listening, if you want to send us an email or text or notify us if you're in the room today that you would like to have a copy of the presentations, we will be happy to email that to you or provide you some other form to make those available to everybody that's interested. Unfortunately, we just, because of limitations on being compliant with ADA, we could not make them available at this time on the web page prior to the meeting. So that's an issue that all of the water boards and all of our documents, so you may see there have been significant changes to our web page over the last couple months, and will probably continue to be in what is available as we are systematically going through and making sure that all of the documents we have available are fully compliant. That's also a little bit of an issue if you want to go back and look at some of the orders that use produced water and the produced water orders on our webpage. Not all of them are currently available because of ADA compliance issue. But as I said, we're systematically working our way through that process, making sure all of those orders are fully compliant And as soon as they are, we are putting them back up on the webpage to transparency. And again, if anybody has a document that they're looking for that they've not been able to access, you can email or contact Water Board staff, and we will be happy to provide those by an alternative method. With that, unless anybody else has anything they want to talk about kind of in the introduction, I'll do the agenda review also, and then we'll move on to the meeting summary for the August meeting. As far as the agenda review, we're primarily going to talk about the 3 tasks that GSI are completing, which are the literature review, the toxicity review, and the fruit sampling. And then, as we talk about that, and GSI will talk about where they are on preparation of their reports for each of the tasks. We'll talk about the white paper. My staff is continuing to work on the white paper. We're building upon it and adding parts of it as we go. We're waiting a little bit for some of the GSI reports so that those can be summarized, probably attached as appendices to the white paper, or at least referenced in the white paper. And my hope is still, although it's a little bit of an outside hope, that we will have a completed draft by the end of the calendar year, which is 7 weeks or so from now. I'm a little bit hesitant to think that we're actually going to be able to achieve that, but that's been my goal for several months, and so we're still working on that, and I'm still pushing to try and get that done, but it may dribble over a little bit, just to be completely honest with everybody. But the draft white paper, when we have it, be reviewed by the panel, because actually it will be the culminary event basically for a lot of this effort. When it is completely done, it will talk about the 3 tasks that have been completed, the work that the panel has done, the recommendations that the panel wants to make as far as how we should proceed with this particular activity, summarize the results and whatnot, and kind of be the final event of this particular effort. And I still believe we're on track to finalize that in the early, at least within the first half. It could perhaps be the second quarter of the 2020 calendar year, but my hope is that by April, May, June at the latest, I'm getting this document on a calendar event to have a presentation to the Regional Water Quality Control Board to present the findings. My personal hope is that that presentation will take place in April, because our April board meeting is going to be in Bakersfield. And since this activity is happening in Kern County, Bakersfield seems like the perfect location for us to have an information item to the board and basically present them the final report and summarize what is in it. And I would encourage everybody who's been involved in this effort in following it that would be a very informative meeting to go to when we make that presentation. I hope that the panel will be able to join us, although it will not be in Sacramento, where most of you, or many of you anyway, are located, so it would be a bit of travel. It's about 5 hours away to go to Bakersfield. But again, I think that will be a very informative. I would anticipate that our board would have a lot of questions and would like to hear from experts in the area that may have more expertise than staff, which is why we put the expert panel to begin with.
Clay? Has
Yes,
a
Bruce.
date been set yet for that?
We have a date. Josh, can you pull up the exact date for the board meeting? I do not have it memorized. And I believe we have secured, I want to say it's in the Kern County Board of Supervisors chambers. I believe that meeting will be webcast. I think we have webcast capabilities there that I think we're working to be able to do that. So if you can't participate in person, you can at least follow it on the web page. Absolutely.
Bill Alio, Environmental Working Group. I missed it. First you said May something. What's
Well,
May versus April?
I
What
hope
was
to
that
have
again?
I hope to have the white paper ready to present in April. That may be a little bit optimistic to get the draft out, get everybody's comments, and have it prepared for April. If we don't meet April, the next board meeting would be June, and that board meeting will be in this room.
Got it.
I would actually prefer to have it in April since this is primarily a Kern County issue. And that meeting will be in Kern County, and we try as best we can to hold meetings in areas where, not to be too remote to the areas where those activities are occurring. But if we can't make April, it'll be June. And if so, it'll be in this very same room. Do you have a date, Rebecca?
Yeah. So the April board meeting is going to be the 16th and the 17th of April, and that's going to be at the Kern County Administrative Center.
Yeah, I believe it's in the Board of Supervisors
Yep.
chambers. They're in downtown Bakersfield. I believe we held a board meeting there once before, a few years ago. But that will serve, usually we have one meeting in Fresno. That particular meeting will be pretty heavy on oil field issues. And so the board wanted to hold that meeting in Bakersfield, so that's the reason why that's there. And since this is related to oil field activities, I'd like to be able to meet that schedule, but we'll do everything we can, but if we can't, then it wasn't meant to be.
Hello, can I interrupt
John?
for a second? Can people hear me?
Yes, Ken?
Oh, hi, this is Ken Clark from the Office of Environmental Health Hazard Assessment. Just wanted to announce that I'm attending.
Okay, thank you. Do we have any other panel members on the phone so that we can document that? I should have asked, I'm sorry. Okay, I'll take that as that we don't have any other panel members on the phone. So let me ask the panel members, are there any agenda items or anything you want to add or want to modify the agenda in any way? And that includes you, Ken. Seeing none, I guess I'll take just a moment to ask if there's anybody that's participating in person, if they have any questions about the agenda or any of the introductory information. If not, we'll move on. Rebecca, I assume we do not have any emailed questions at this time? And with that, I'll introduce Robert Schofield and Bernie Beckerman from GSI. I guess we need to do, the August 29th meeting summary. Josh, you want to do, or Rebecca, do the meeting summary?
Sure. So on the 29th of August, there was a public meeting of the Food Safety Panel in this room. During that meeting, presentations were given on the white paper and the chemicals of interest list. A summary of that meeting has been provided to the panel for comment. After the comment period, we will post a summary of the meeting to the webpage after it's been made ADA compliant. There is also a video of that meeting on the webpage currently for those that would like to see it.
Do the panel members have any questions about the summary? I mean, certainly I don't want to put you on the spot and let you, but if you had any questions at this time, we certainly can entertain those. Otherwise, we'll move on.
Clay, we did
And-
have one question online as to whether or not we were going to send out the presentations, I guess, to the Lyris list. I would suggest that we do that after the meeting and we PDF them.
We can do that.
Okay.
Make that so, please. So if you're on the Lyris list, you will be receiving a copy of the presentation. And for anybody that's not on the Lyris list, if you want to send information, we'll be happy to tell you how to get on the Lyris list or send them separately if you so desire. With that, we'll move on to the task 1 information. And Dr. Bernard Beckerman from GSI can present the information that they're working on.
Great. On this screen, it's waving like it's underwater. It's a little distracting. Yeah. Oh. Well, that was much better. The flickering is fine. All right. Well, thanks for having us here. I'm going to briefly discuss the 3 tasks. Briefly discuss at least the first 2 tasks. And in a little more detail, discuss the crop sampling and the analysis that we're currently working on. And so just as a reminder, the first task we were asked to assist with was identifying the list of chemicals of interest based off of the list of additives that are known to potentially be used and be present in produced water, and then also add to that and identify potential naturally occurring chemicals that could be present in produced water. The second is a literature review based off of our evaluation of those chemicals. And the third is an evaluation of the analytic results from crop sampling. So in identifying the chemicals of interest, I mean, we've come a number of times and presented on this, and so I'm just going to present a very brief overview on the work that's been done and where things currently stand. So I'm providing here a little bit of a roadmap, and what this shows is we were provided with 347 additive chemicals, and this was as of June 2019. We identified 90 naturally occurring chemicals. 45 of them were organics, 45 of them were inorganics. As you can see in the graphic, through steps 1 through 5, this represents sort of the research that we've done. In the first step, we identified those chemicals with published toxicity values. There was 107 of them. And from that, we were able to identify 23 chemicals for which we could use read-across assessments. In the second step, we identified those chemicals where we had little concern for chronic oral toxicity. These were things like constituents in food, things that we knew to be considered non-toxic, food additives, those which are used for therapeutic oral use, destroyed in water or inert. In the third step, which is sort of the really major research step, where we reviewed the remaining chemicals to identify what other toxicity information was available. And from that, we identified 60 which would require further information because they didn't have any usable chronic toxicity data. The remaining chemicals, we identified 69 where there was no evidence of chronic toxicity. 15 of them, we had a difficult time in making a final evaluation, either because some of the data was conflicting, or we had a difficult time just identifying what the chemical was based off of the additive names and information we were given. And for 51 of the chemicals, we developed what we're calling ad hoc surrogate toxicity values. And this is based off of normally either some published data and other are government reports where, for regulatory reasons, chemicals needed to be tested. there were animal tests done to evaluate their toxicities, and based off that information, we developed very similar toxicity measures to those with the published toxicity values, and we were able to sort of develop a evaluation procedure to look at all of those chemicals together. So after this large research work, we screened the chemicals to identify those which were of highest priority. Of the 180 chemicals for which we had information, we chose those chemicals which had toxicity values that were less than 0.5 milligrams per kilo per day. And this was based off of some very generalized conservative consumption assumptions about how much fruits and vegetables people consume and how much would be required of any given chemical to be ingested based off of those consumption patterns. And also choosing those that are poorly biodegradable or inorganic. After that screening, we identified 65 of the 180 that we identified as chemicals of interest. 39 of those are attributable to the list of additives, and 35 are attributable to naturally occurring chemicals. There's a little bit of overlap, which is why if you add them up, you actually get 75 and not 65. And then additionally, as part of the literature review, because we're missing some information, we went and further evaluated through the literature 60 chemicals with the insufficient data to identify chronic toxicity, 15 chemicals with incomplete information, or those that we had a difficult time even identifying what they were, and then the 5 radionuclides. So that basically summarizes where we are. We currently have a penultimate draft that we will be sending out to the food safety panel for their final comments, and then hopefully have that prepared and ready, ADA compliant, to be posted online. So that moves us into the second task. I'm going to take a break here because on the agenda, there's time here to ask questions if you have any.
This is Ken. I had a quick question.
Yes.
What are the 5 radionuclides?
Uranium, radium 226 and 228, and then xenon and I believe argon, 2 radionuclides. I think those last 2 are tracers. They produce beta radiation as opposed to alpha, gamma, and so it's a little unique in the natural environment.
All right. Okay, thank you.
You're welcome. Okay, moving along to task number 2, the literature review. So as was proposed in the scope of work, we were going to try and develop some systematized means of reviewing the literature. And the first part of that was developing a guiding question. In this case, what is our understanding about the use of produced water to irrigate food crops in the context of hazards to human health that may be created by the use of this water? And additionally, as in evaluating literature, we need to sort of identify how well we can extrapolate what may be generalized but applicable data to sort of the specific context of agricultural irrigation to food crops. And an example of this would be looking at information about how people have used produced water and treated it for drinking water, or used produced water for things like watering cattle or other animal crops, and does that translate to the kinds of health concerns or hazards that might be associated with human consumption of vegetative crops. And so in the systematic review, part of it was identifying which kinds of literature and the degree to which we might be able to trust the literature. So we have 5 main evaluation factors. The first was date. And so when it came to literature focused strictly on the use of produced water, we tried to focus on those pieces of literature which were 2000 to present. We had no restrictions set on other literature, in part because of sort of a lack of literature, but our goal overall was to focus on most up-to-date data. As far as methods of extraction go, those which were used for onshore oil and gas production and for both conventional and hydraulic fracturing those that were looking at the use of produced water in North America, literature in English, and the types of publication are here are reported in sort of the hierarchy where peer-reviewed literature is looked at as having been most most reliable, and those of industry reports being least reliable. So I realize it's a little bit small. Hopefully you can squint a little bit and make out some of the text. What we have are 9 sections that we've identified as the framework for a literature review. The first is going to be the introduction, which reviews conventional, non-conventional produced water in the context of agricultural irrigation. Next, we're going to review the available water data that is being posted by the Water Board and is currently being updated for 2019. We're looking at what are the ambient levels of these chemicals in air, water, food, and soil. Other sources of these chemicals with a focus on agriculture, but also other sources. The chemical toxicities, and while there has been some discussion in Task 1, we're presenting a bit more of an expanded discussion on some of the other health outcomes, including endocrine, teratogenic effects, and some discussion of the epidemiology. And this will include a much more extended discussion of those where we had ad hoc surrogate toxicity values. A more expanded discussion on fate and transport, not just in water, but also in soil, breakdown products, and then a more focused discussion on breakdown products, where are the potential knowledge gaps, which is actually the majority of that discussion, is unsurprising to us after having a number of meetings here. And then a discussion of plant uptake. And this tends to be a bit of a more general discussion because the combination of plant and specific compounds and the rates at which they're uptake and to where those compounds locate are very specific to the plant and the conditions for which it's grown. And then obviously the knowledge gaps at the end. So the majority of our raw research is complete. We're sort of continuing work, waiting on some updated data to review the water data. We're working on synthesizing, writing up this information, identifying our knowledge gaps, and also classifying the compounds based off of the information we have in feed and transport. So that sort of summarizes where we are currently. You have any questions, comments, suggestions? Yes.
When you're talking about classifying the compounds, can you give us a little more idea of how those classifications will work?
Okay, so something, say like some of the PAHs, which are planar, the way they'll behave in the environment will be that the ones stick together. So because they're kind of like plates, they will stick one on top of each other, and then they'll also stick to organic matter. So we have a good idea of the kind of mechanism which may attenuate the ability of those to locate or be even available to different kinds of plants, where things like metals, given a standard environment in which a plant is grown, may be more likely to move within the soil and then be taken up.
Come up with.
Well, they'll be classified according to sort of those groups of like natural groups of the planar, things like planar compounds will be grouped in. They'll have some expected interaction with the environment. And so that will give us a class of these chemicals. Some of them are going to be like metals. They will move within the water. They'll move with the water, especially if the water is acidic. And that's going to be sort of a separate class of chemicals. But we have a larger number of chemicals that sort of behave in potentially mixed ways. And so that's how we're working on classifying them.
Whenever I try to categorize things like this, the categories don't work out. So.
Yeah, I mean, they're a little bit, in some cases, they're not solid categories, but they do give us sort of a spectrum of how we might expect these compounds to interact with their environment, from being in the water and then all the way through to being applied to the soil. Are there any questions, comments, suggestions? Yes.
Just a quick question, based on the sort of discussion you're planning to have on breakdown products and transformations and whatnot. So how are you gonna do that in a way that doesn't take you down an enormous rabbit hole with going chemical by chemical? Or are you just gonna have a few specific examples as cases, or it's just it's just a very big topic which can be not necessarily solved in a chemical by chemical approach, I think.
You're absolutely right. And I mean, honestly, where the work has shown us is that the environments are very specific to how the chemical breaks down, and that there are a few cases where we are able to we have a good idea that some of them may not entirely mineralize under bacterial degradation, but for the most part, we don't have enough information to be able to determine what those breakdown products are or how they may break down, if at all.
Thank you.
If I may just add one thing to that, is I am working with them, and we're talking about, this is a big issue, and trying to figure out, also looking at how other, some scientific studies that are being done and other approaches taking for whole water sampling for things like toxicity. And I'm consulting with them on, just make sure we're trying to cover all the bases as best we can. So if people have suggestions of things that we need to look at, now would be a good time to put it forward.
Yeah, I'll just offer myself as well if you want to talk about some of these more holistic approaches to identifying toxicity and, non-targeted sampling approaches. I'm happy to hop on board.
Okay, great, thank you. All right, so moving on to task 3. This is going to be some of the more detailed discussion here. So just a brief overview of what I'm going to be talking about. I'm going to present the crops that we've sampled, sort of the analytes that have been tested, the results of that testing, and a little bit of discussion and where we're moving forward in the future. So to date, we've received all analytic results for the crops that have been sampled. The table on the right-hand side reports all those crops that have been sampled 2018 through 2019. I'm not going to go through and read them all. And we also include in this analysis all of the previously sampled 2017 data. And so that's for almonds, garlic, grape, lemons, mandarins, navel, pistachios, and Valencia oranges. So what you see here are sort of a generalized overview of all the results that were detected. We tested for 113 analytes. 18 of them were metals, 95 were organics. The majority, what you're seeing actually is the majority were not detected. Most of the detections we saw were metals, and there were a total of 30 unique analytes. Now, to decipher this gigantic blob of a square here for you a little bit, you can see there's a bit of a columnar format to it. Each column represents the analytes that were tested for in each of the crops. Where you see light gray, those were the analytes that were detected. Now, what I want you to see mostly from this is that most of the things that we tested for, we did not find. Now, there are some that you see seem to be right across the board. Like if you go from left to right, it looks like there's a few things that were detected in everything, and that is absolutely true. We saw things like copper, strontium in every sample. Not unexpected, but kind of what we ended up seeing in the end. And so what I'm going to do right now is sort of go through each of the 30 analytes that we detected, make a brief discussion of them, sort of discuss sort of like how much we saw of each in our samples. So I'm going to talk a little bit about the metals first, and here we have strontium detected in 257 of the samples. It's pretty common metallic elements found in soil and water. We understand a little bit about what our tolerable intakes are at 0.13 milligrams per kilo per day. We know it's pretty common, but we don't have very good quantitative data to understand what we might expect in all of our crops. Copper, again, seen in 238 of the samples, common element. It's known to naturally occur fruits and vegetables, normally at the range of 1 milligram per kilo, but it's particularly high in nuts, upwards of 15.5 milligrams per kilo. Barium, another common element seen pretty often. We have a typical range that we might expect. Zinc, again, another common element and a basic nutrient, occurs in a lot of food. We have information on tolerable limits in both infants and in adults, upwards of 40 milligrams per day. Nickel, some of the highest nickel that's normally observed are things like oatmeal and spinach, asparagus and peas. Nuts are also known to have pretty high levels. Antimony, it's reported to occur in food generally in the range of 0.2 to 1.1 micrograms per kilo, but it's observed very high levels similar to that observed here, very related to soil conditions. We understand the tolerable intake levels at about 6 micrograms per kilo per day. Molybdenum, typical range is pretty high at 1 to 2 milligrams per day, or 1 to 2 milligrams per kilo. Chromium, we have a bit of an understanding about the sort of quantitative levels of 20 to 190 micrograms per kilo. Cadmium levels are upwards of 124 micrograms per kilo, and we sort of have a good idea of what tolerable intake levels are. Cobalt, pretty common in fruits and vegetables. We understand sort of basic intake of cobalt is upwards of 40 micrograms per day. Vanadium, another common element found in foods, sort of tolerable upper limits of intake, 1.8 milligrams per day. Arsenic, very common, especially here in California. It's been reported in grains and fish to be between 20 and 140 micrograms per kilo. We do observe it in one set of carrot samples at trace levels. The range of expected concentrations when they're not grown in contaminated soils hasn't been well quantified. But the levels here that we're observing, at least in the trace levels, seem to be a little bit higher than the total food study. But that has to be given the caveat that the total food study doesn't necessarily represent the food that we would normally eat every day here in California. The drinking water standard, just to give a little context, is set at 10 micrograms per liter, or basically equivalent to a dose of 20 micrograms per day. And then lead, another common historic element contaminated, having contamination of soil caused by leaded gasoline and lead arsenate pesticides. We have a small amount of lead that's reported in fruits with a typo, which I apologize for. The total food study generally reports low levels at 3 to 4 micrograms per kilo, and sweet potatoes a little bit higher at 12 micrograms per kilo. But otherwise, last is selenium. And there's been some discussion by WHO about setting tolerable upper intake levels, and that should be around 400 micrograms per day with little risk to human health. So moving forward through to the organics, and I believe there are just about as many. You have acetone, sort of used as nail polish remover or for other industrial uses, but it is known to naturally occur in fruit. Our understanding of the quantity that might occur in fruit is not very well fleshed out in the literature. Acrolein, another naturally known occurring compound in fruits and vegetables. WHO has set a tolerable limit up to 7.5 micrograms per kilo per day. A large amount of your intake comes from things like fried food. We have ethyl acetate. While used as a solvent, it is what has the fruity odor in your fruit. And in very ripe fruit, like very ripe apples and guava, upwards of 8 milligrams per kilo. P-isopropyltoluene is a naturally occurring compound used as a direct food additive. It has some industrial applications, but a large amount of your intake comes from pretty common foods like butter, carrots, orange juice, oregano, raspberries. And even the levels that we see in fresh orange juice can be upwards of 250 milligrams per liter. And then methanol, common byproduct in fruits and vegetables due to the breakdown of pectins. There was one study we found where after just 1 hour of having blended tomatoes, the juice had levels upwards of basically 100 milligrams per kilo of methanol. Butanone, I'm sorry, I apologize. Like, I know this seems a little bit, but we see the next step is a lot of results, and I want to have a little bit of context to these because it's going to hit you a bit in the face when you just see big tables of lots of numbers and a number of these compounds. So we detected butanone. While a common industrial solvent, it's also very common in food, pretty high levels in legumes and other commodities like nuts, cherries, and cheese. We did identify like MTBE or methyl tert butyl ether in pistachio samples, the most recent pistachio samples. They were identified in all 11 of 11 pistachio samples, but the results don't seem to make any sense in the sense that they're all nearly exactly the same level in both treated and controls. And MTBE has not been used in California since 2003, I believe, as a basically oxygen enhancer in gasoline. We're currently still working a little bit on QC-ing that data. We did run some QC with the lab, and they couldn't identify the reason for that. But there's also the potential that it was just misidentified in the chromatograms in the spectra. It's not something that hasn't happened in the past where I believe previous 1,2,4-trimethylbenzene had been misidentified, and it was in fact D-limonene, which is a very common terpene in oranges. We identified it was identified 2-hexanone. Again, the concentrations in vegetative crops are not well understood, but it has been measured in other food sources. Methylene chloride was identified in 6 samples. Not exactly expected to be in food crops, but these things just kind of happen sometimes in lab samples. We see it in 4 of the control samples and 2 of the treated samples at relatively low levels. Bis-2-ethyl hexylphthalate is a plasticizer. It's pretty ubiquitous in the environment. It's known to be seen in food, but not naturally occur as just a sort of an ambient contact. Then we have phenol. Again, not something that's expected to be seen in food, but the levels are low, and they're only observed in 4 of the citrus samples. We see 1,4-dioxane in 1 of the control samples, used as a solvent. 2-chloroethyl vinyl ether is seen in 1 of the treated samples, but while it's used in some industrial applications, it's also used as a hormone regulator in plants, and so it could be used to control ripening. That might be its source. We also see a couple of PAHs in 1 control sample each, benzoapyrene, dibenzo AH anthracene. They could be just contamination from a nearby tractor that was driving by an orange or something. And then sec-butylbenzene is another pretty common environmental contaminant. It could have just been due to some contact. So just to tee up the analysis a little bit, and to give a little bit of background, the previous analyses have focused on identifying statistical differences in means. However, here, because we had a lot of non-detects and many of the samples were pretty small, it wasn't really a feasible option. And so instead what we did is we focused on identifying if there were any differences in the number of detections. So are there differences in the number of controlled detections versus the number of treated detections? And by treated and control, if I didn't make this clear, treated being those that were irrigated with produced water, and control those that are irrigated with sort of conventional sources of water. And so to conduct this test, we used what's called the Fisher's exact test, and we did some adjusting for multiple testing, which I'll explain a little bit later. But the Fisher's exact test looks to determine if there is an association between two categorical variables, and those categories would be control and treated. What the test does is determine if the proportion of one factor, in this case, whether it was detected or not detected, is different between those two categories. And in identifying or in interpreting the test result, you can think of if the p-value is less than 0.5, it indicates evidence of statistical difference between the groups. We can talk a little bit more about what the actual test is, but what it's able to do is it looks at the proportion of detects or non-detects based off of what are the marginal sums here on both sides, looks at all the potential combinations that those marginal sums could apply, and then determines whether or not the proportion that we're observing is basically implausible given the potential combinations. And those that are more, if it's more implausible, it will have a lower p-value and basically indicate that the difference is statistically significant. So into the results, I'm going to start this off sort of as to say that I'm going to describe in detail the first line, and then as I move through all of the crops, because there are a number of them, point out specific things which may be of interest, but I'm not going to go through each line of each table individually because I think it's sort of wastes everyone's time. So starting out here, I'm going to use the pointer here, looking at acetone, and this is for the almond results. We have two lines here for control and treated. Big N here is the total number that was in that sample. Little n are the number of those samples that were detected. We have a T here, and this represents the trace, whether the detections were at trace levels. And what that means is there are two basic quantities when conducting these analytic tests. We have what are called detection levels and reporting limits. And so a detection level will tell you whether or not that compound is, or the limit at which you can determine whether that compound is present. Then the reporting limit is a level at which you have a certain certainty that the quantity that you're providing is relatively valid. And so what we see here is in this table, there are no trace levels that were observed. So everything was above the detection limit and also above the reporting limit. You'll see that's not the case later on. And then here, ND here are the number of non-detects. So I report here the range and the detection limits and the reporting limits that have been provided to us by the labs based off those results. And then min, max, and mean here are the actual based off the analytic results provided by the lab. We have the minimum concentration, the maximum concentration, and the mean concentration in milligrams per kilo. Now the mean concentration, because we have so many non-detects, what we did is substituted all of the non-detects with 1/2 the detection limit and then calculated the mean based off of the full 24 sample. In this case for acetone, or for the almonds, it'll be a different number total in other samples. Now, this here are the results of the Fisher exact test that I talked about before. And I'm going to talk a little bit about these adjusted p-values over here right now. So when making tests with lots of tests at the same time on the same piece of data, there are concerns that by random chance, you're going to get a result that shows that you have a statistical difference. And that's just by random chance. And so when we use this 0.05 value, basically what you're saying is that if you were to conduct this test 100 times, you would expect to get the wrong answer 5% of the time. And so you want to be within that sort of level. Now, if you conduct that, and that's if you only conduct one test, but if you conduct those 100 tests a number of times, you're going to get that wrong answer a lot more times, and especially because we're using the same piece of data. It's not independent. So what are reported here is FWER, which is a family-wise error rate, or FDR, which is the false detection rate, are two different methods that we use to adjust for the likelihood that we make this wrong inference. And so if you see here, we have the Fisher exact test p-values ranging from 0.11 up to 1. Again, here, we're not seeing anything below the 0.05 sort of criteria level. But after adjusting for the potential for these either family-wise error rates or what are known to be the false detection rates, we now see that those p-values are much larger, don't indicate that we have any statistical difference in the number of detections. Just want to make sure everyone's comfortable with that at this point, because we're going to be moving now through a lot more of these samples. Now, if we just sort of very quickly look at the results, and I'm not going to sort of read each one out, on the whole, we don't see a lot of difference in either the min, the max, or the mean. They're all in the same general level of magnitude. In some cases where we have, say, for methanol, we see one detection in a treated, but not in a control. But otherwise, those orders of magnitude and detection are all very similar. So moving on to apples, there were 4 samples taken. We saw acrolein, copper, ethyl acetate, and strontium. And back from those previous slides, these are all very common things to be seen in fruit. We don't, unfortunately, have any control samples, in part because this is a very minor crop. There weren't any available at the time. But we don't see anything that sort of screams at us as being outside of the norm. Next one is carrots. I think one of the things that, after going through 3 slides, that should become pretty apparent is that we see different numbers of analytes detected in these different crops. It's going to seem, once we put this in a little more context, this is going to seem a little bit, have a bit of a different flavor here too. But what we see in blue, or slightly, for those of you who, difficult to make out the blue because it might look a little bit gray, are those analytes which are in blue also have that T qualifier in it, or the trace identifier. So the concentration that are reported are above this detection limit, but below the reporting limit. So we know that they're there, but our confidence in the quantity that's reported here is not up to sort of the required standard to meet that reporting limit. What we see are arsenic, cadmium, chromium, cobalt, copper, lead, molybdenum, nickel, selenium, vanadium, and zinc. I think one of the things that is sort of important to see here is that while we see trace amounts, if we look at those things which are not detected in trace, at trace levels, we see about the same number of things that we would normally detect in most of the other compounds. It just happens to be this one particular sample had low detection limits, and they detected very trace amounts of these compounds, not outside of what might be expected in food crops. There was also, this is the one sample where we saw 1,4-dioxane, but only in the one control sample. I mentioned that now because I mentioned it before while talking about the different compounds. Moving on to cherries, we had a pretty small sample here with only 3. Cadmium was detected in both treated and controls, but only in one sample, and then copper and strontium in everything else at levels which are well within what we've seen in everything else. We have garlic. A few more compounds here detected. We see a bit of the case where a lot of things seem to be detected in controls over treated. So we'll have maybe one detection. So one detection of bis 2-ethylhexyl phthalate, one detection of chromium. In this case, 3 detections of ethyl acetate, not uncommon in fruits and vegetables. 4 detections of methanol, 3 detections of nickel. If we look at the Fisher's exact test, and maybe I should go back, and I apologize, I should have gone through this. As we go through the Fisher's exact test here in the carrots, we don't see any evidence of statistical difference. So even before adjusting, there's no evidence that any of these are statistically different. And the same goes for cherries. And for garlic, we see a similar pattern, no evidence of statistical difference. None of these values are less than 0.05, and after adjusting for potential multiple testing issues, they're much larger. Moving on to grapes. What we see here, antimony here is detected in one control sample, not in treated. Levels otherwise are all very similar, sort of within the same order of magnitude. The Fisher's exact test before adjusting for multiple testing seems to indicate some difference in the strontium, with 20 detects of strontium versus 12 in the control. But after adjusting for multiple testing, we see that that difference does not appear to be statistically significant. For lemons, what we see here are that, that's sort of interesting. In barium, we have 5 detections in controls, none in treated. 2 detections of methanol in controls, none in treated. 3 detections of phenol in controls, none in treated. When looking at the Fisher's exact test for this, we see that barium appears to have some evidence of statistical difference, but after controlling for multiple testing, there doesn't appear to be. But again, the levels, when we do observe them, they don't appear to be significantly different from each other. Okay, for mandarins, this is the one sample where we saw in one benzoate-pyrene detected in a control, dibenzo-AH-anthracene detected in control. But otherwise, mean values are relatively similar and in the same order of magnitude. The Fisher's exact test does not appear to provide any. Sorry, I thought I saw a hand up in the, but not. The Fisher's exact test doesn't appear to show any evidence of difference, either before or after adjusting for multiple testing. And this one also had the one sample in the treated which reported sec-butylbenzene, but that hadn't been reported in any other samples. Navel oranges, similar patterns. We have the 2-chloroethylvinyl ether, which is that potential hormone regulator that was in one treated sample. Otherwise, the levels are all within this sort of similar concentrations by mean. Fisher's exact test doesn't appear to show any evidence of statistical difference. know, here in pistachios, what we're seeing are one detection of antimony in a control, one detection of bis-2-ethyl hexyl phthalate in a treated, 2 detections of methylene chloride in a control, 1 detection of molybdenum in a control. Though overall, the differences that we just sort of observe, while not statistically, why we can't look at them statistically, don't appear to be much different. Looking at the Fisher's exact test based off of the detections doesn't appear to be statistically significant. And sort of similar results with tomatoes. Mean values or estimated mean values are all very similar, and there doesn't appear to be any statistically significant difference in the number of detections. Valencia oranges, we have Valencia oranges, we have a detection of phenol and a control, but there doesn't appear to be any statistical difference in the number of detections overall, and levels are all really similar. And then if we look at this on the whole, and do a similar review, first thing I want to point you to are sort of these grand totals. And if you look at sort of where we see sort of continuous entries of numbers, things like acetone, acrolein, copper, strontium are basically filled directly out, and these are reflected in these grand totals. Now, if we do similar Fisher exact test now in the entire data set, we see maybe before controlling some evidence of difference in strontium and phenol, but after controlling for multiple testing, there don't appear to be any statistical differences. I'm going to stop right here and open it up for some specific questions related to the results so that we're not moving too far forward, and then we can maybe discuss here, and then I'll move. Are there any? I know we just sort of plowed through 12 tables, I think. So if you want me to go back, I'm happy to go back and discuss some specific things. Yes. Oh, Mike.
Well, I guess I'm holding it and I shouldn't be, sorry. I noticed that a lot of your somewhat lower p-tests are actually where you have lower levels in the treated than the controls. I don't know how you indicate that in the chart, but that would probably be helpful to the reviewer who's looking at it. Because I don't really see any treated samples that are hanging higher even before you get to the quantitative analysis. Is my impression of looking at this data.
When you say higher, what value are you talking about higher? Just the number of detections? Or the
Number of detections or larger levels or farther away from the reporting limit, or, you know. I'm just not seeing anything here. I'm coming to the question for you is, if you had to take a take-home message about the treated water here, what would it be?
Well, as far as the take-home message from this review here, does not appear to show that there's any difference between the conventionally irrigated crops and those crops that are irrigated with produced water. They, on the whole, appear to have very similar levels of detection, very similar levels of the actual compound. It's hard to make definitive statements about statistical difference of the levels just because we have very small samples in a lot of the cases. But using sort of an order of magnitude test, if we might expect some source of water to be the culprit in determining the levels that we're observing, we might expect to see at least a 2 to 5 to 10 time difference in the levels that we're observing, but that doesn't seem to be the case. They're all within 20% or less. which is well within what might be expected just for soil levels or sort of ambient or other ambient sources of these chemicals.
Well, that's kind of what I was thinking here, because these aren't from oranges off of the same tree, the control and treated. They're similar environments, but I'm surprised we aren't seeing more differences, frankly.
Mm-hmm. All right. So take home here is like overall, there doesn't appear to be a lot of significant difference between the treated and control samples that you could directly attribute to the source of the irrigation waters. We did see some unexpected chemicals, and actually more often in the controls than in the treated, but we did see crop ripening agents, some common laboratory solvents, which may have been a result of sort of issues with the lab, which are pretty common even in other samples, and other ambient chemicals which may have been introduced into the sample. So currently our ongoing work looks at identifying hazards associated with the consumption of these crops. So this includes identifying those likely consumption patterns, estimating the dose that results from that consumption, comparing it to quantity of food that would be required to reach some criteria dose that would be related to the work we've done in task 1, and then looking at whether the information we have on the actual irrigation water quality seems to play a role in what we're observing here. And so that's where we currently are. A large part of this is written out, but we're finalizing this final part of the analysis. Yes.
So do you subtract the values you see in the control water in order to get some level of impact from the treated water? And if so, how do you treat with limits of detection and things like that?
And the answer to that is no, because the samples are as small as they are, it's hard to say that the difference we see is attributable to one or the other. And you're potentially introducing sort of an uncontrolled bias into the estimate if we try and subtract one from the other and then say that's what's attributable to one, because we don't have any evidence that that's the case.
But that's the question we're being asked, I think.
It was our understanding that the question was, is there a difference? And it appears that that difference is no, given what we're able to do with the data. But I think trying to subtract one from the other is difficult, given that there are other factors that may be involved in why we're seeing the difference. I mean, if the differences were on the order of 5 times and 10 times, I think we'd be well within what would be reasonable to say subtract one from the other and say, okay, this is the part that's from produced water, this is the part that's from conventional water, but they're very close and we don't have enough information on tillage practices, on what's applied to these crops, on what's in the other water source. Those other surface waters, are they coming from groundwater as well? And what are the soil conditions? And so there's a number of factors that seem to be enough to represent the very small differences we see, and we don't have a way to say, get rid of that difference, those confounding effects in making estimates of what are attributable to one versus the other.
Question.
Yeah.
Sorry, I gotta get closer. So in follow-up to that, Steve Beam, Department of Food and Agriculture. So then the ongoing work that you describe here, and you talk about estimating dose related to likely consumption, and then comparing these to quantity of food required to reach a criteria dose. Is that for the chemicals identified, chemicals of interest, and the literature review? Because what I'm hearing you say is you don't have enough information to make a distinction between the treated and the control. So if you pool all the data and get an aggregate number, you're basically evaluating something that doesn't really get us to a decision point. It might be of interest, but it's not really at the question we're after. So Could you clarify for me what you mean by this ongoing work and the reference dose information here? Is that for the other things that you're talking about?
That's for those things which we've actually detected in the compounds. And so, I mean, we have things like reference doses or cancer-specific like risk-specific cancer doses based off of the task 1 work. Now, we use that as sort of a library or a database of values which we can then use to evaluate those things which we have detected. But we can't evaluate things we haven't detected. Like, I mean, there's nothing we can do in that case. But we will use those same values and potentially other literature if it makes sense, given the food crop, the kinds of consumption, the effects that may have on the dose in your body and what that particular compound is in reality in the crop. But we're not evaluating all of those compounds because we've only detected 30, some of which aren't even on that list.
I guess it's getting back to your comment. I'm not sure what we gain by if we don't see a difference between treated and control, and then you're combining the data to come up with an average number to use for this reference dose information. That gets us information about what that particular analyte might mean from a public health significance, but it doesn't do anything with respect to guiding us in whether the produced water use is safe or not safe. So I'm just wondering what that's really doing for us.
Can I add to that? I think that the
Thank you.
issue came up before where we said, is there a difference? And in some of these cases, it's really hard to see there's any difference between treated and controls. And so when we tried to look closely at what's the average concentration, we realized we've got so many non-detects in here, it's really hard to come up with a valid mean estimate. So in this next step, what we're starting to do is to say, okay, we've got these certain concentrations of metals, say, in a crop. And then the next step, we're saying, how much of that crop would you have to eat if you had the mean or if you had the max level? Just to give us a sense that, okay, you couldn't eat enough almonds to get at the reference dose for strontium. So that we know that's getting at the safety question of, okay, how much of this would you have to eat to get at the reference dose? But I agree, when we thought about could we stop at the point to say, look, there's no difference between the control. We have no reason to believe there's a difference between the controls and the treated. We're done. But to make sure we nail down the safety question, we're going to go ahead and do this. We've started doing these evaluations of how much would you have to eat to get to the point. So we're showing that there's no difference and the level that is there is safe. So, and maybe the second step isn't needed because of the results of this first section just show there's no difference.
Well, I think
Thank you.
especially what I'm taking from this is if the guidance comes, you should buy your produce from plants grown without treated water. And I could see that coming and that going into the organic standard, for example. You're not changing the person's intake. So you're you're possibly adding something here which the data don't drive us to do. So I think we just need to be careful. And I understand the problem with subtracting the controls, though that's the obvious thing to be done. But you know, I understand because we try to do this, and it does get you into a problem from the statistical end of it. But
Yeah, if we were trying to say, yeah, there's a little bit more of each chemical in the crops that are treated with the produced water rather than just regular irrigation water, and we'd say, well, does that difference matter? Yeah, there's a little bit more, but it's safe. It doesn't matter. But that's not where we are. We're at, okay, we can't see any difference. But I can understand when you look through those tables in detail, in some of them you'll see the small difference that Bernie referred to. Well, sometimes the mean concentration is a little higher in some treated, sometimes it's a little bit lower. So I think our conclusion in the end was there's no real difference. But we realize that there are some differences, and so people might say, well, I see a small difference in, a little bit more in this treated crop. So we wanted to put the whole thing in perspective to say, okay, even if that difference is real, there still isn't enough in there to get
But
you to this reference dose.
But I think your Fisher test says we're miles away from anything being different here. I just don't see anything there that says to me, go get more samples or go do more analysis.
I think that's our conclusion as well, is we don't see any real, there's a couple of them that Bernie pointed out where the p-value was less than .05, but in some cases it was the control was higher, or we had more in the controls, as you pointed out. In some cases it was a little bit higher, but we wanted to say, okay, but even so, you're just not going to eat enough. You know, if this is real, you're just not going to eat enough of this particular crop to get to a point where it's of concern for health.
And let me interject something, because this is Clay Rogers with the Water Board. The task of the panel and the task of GSI is to determine whether or not there's any actual difference associated with the use of produced water. This isn't an overall risk assessment of different types of food grown in some area. So the big issue to me is there a difference? And not so much the follow-on work. Because if there is no difference, and it looks like we're within the natural variation, I mean, we've even seen where we ran duplicates that, you know, you don't get the exact same answer, even if you run the same sample through the analytical tests. So, you know, and there can be issues associated with different parts, you know, may actually have different concentrations, different parts of the fruit. So we have those variable questions, but where we don't see any difference between the treated, which is irrigated with produced water, and the control that is not, the operative question to me, and I think the task that basically I and the Water Board itself assigned to the panel is, are there issues associated with the use of produced water over and beyond the use of other sources of irrigation water? And to me, if the fruit samples in the treated and control are essentially the same, which I believe is the determination we're coming to, I tend to agree with Stephen and Barbara that we, you know, the additional work associated with going through reference doses and how many almonds do you need to eat in order to reach the reference dose may not be within the scope of what the panel and GSI have been tasked with doing. And so I'll just ask the panel, is there general agreement with my statements? Because as I understand it, you know, and the task that I think we assigned was, is there a problem with using produced water? Does it increase risk? If the answer to that is no, that basically we see the same results. Granted, it might be nice to have more samples of certain crops, but some of the issues like the apples, there's just a few acres of apples, you know, and there's not really even any other apples grown in Kern County. So it's a very, very small crop compared to the overall acreage of that commodity, even within California. So I'd just like the panel's thought about that.
Well, this is Bruce, and I would concur with three of you on this one, that we were looking to see if there was a difference in what the crops had in them based on the different sources of irrigation water, and we're not seeing anything. I don't think, I have to agree, I don't think we need to go further in terms of estimating what, you know, how many pistachios you'd need to eat to get something. That's not the question for the panel.
Hi, this is Ken from OEHA. I generally agree with the discussion, but one of the things that I would like to see in terms of the statistical calculations would be the use of a version of Fisher's test, which has got more statistical power, and that would be Fisher's exact test with a mid-P correction.
Sure.
And this is Dave Mazzara, Department of Public Health. I agree with what the majority of the panel members are saying, and Clay as well. Our task was to try to identify differences between the control and treated. I think we've gone pretty far along that pathway and have some pretty good information to inform us on recommendations for the white paper. It might be interesting to look at what the calculations of how much food you need to eat to reach a required reference dose or other type of criteria dose would be. I suspect a lot of them would be very large quantities of food.
Yeah, like probably
which
tens of thousands.
I'm not sure how informative that ultimately is. 500 pounds of almonds might sound interesting and tell people, well, there's really no risk there because you're not going to eat 500, but I don't know if it really helps us. So I would recommend we also don't add that into the total, into the ongoing work.
Yeah, and that's where it comes, where it's valuable, is because we've done the preliminary calculations for most of these. So when you come across somewhere you have to eat 20 or 30 kilos a day, it's crazy. For some of the others where it's helpful, I think, is if you've got a small difference and maybe the treated is a little bit higher concentration than the control, and makes you wonder, well, how sure am I? Then if you say, okay, I need to eat 30 kilos, it really doesn't matter if there's a difference there. I don't really need to hang my hat on the fact that there's a 10% difference in the mean. But most of the results do come out, as you're saying, that you have to eat really large quantities. But there are some that are kind of closer calls where it is good to go back and see how much would you have to eat. A few. I mean, it's pretty much not much difference is where we're coming out. Not much difference in treated versus controls.
This is Seth Shonka from PSC and UC Berkeley. I agree with the panel and with Clay using this particular type of criteria and approach. It's clear that there are no significant differences between treated and control. And using those criteria, I think that the question has been answered. The only thing that I would add on top of that is a discussion of limitations. We've talked about how identification of parent compounds, additives, for instance, that are used, the idea that you would, when testing for those, that they would still be those parent compounds, I think is highly suspect, that they be conserved all the way through from the oil field to the agricultural field. So that is a limitation. I think maybe it's not a huge limitation, but it's a limitation worth noting that some portion of these non-detects could be because that parent compound is not actually that parent compound anymore. It's broken down into something else. And so maybe testing water and especially fruit for those particular compounds, of course you're not going to find it. Complexity of testing food versus water. We've talked a number of times about how we have enough problems trying to test water for, constituents of interest. And the science, and the lab capabilities of testing fruit and food is more challenging. And then finally, I would say that, again, I agree with the panel. I agree with Clay that using the criteria that has been set out to evaluate this, from a crop perspective, I think it's clear, given limitations, that there is no statistically significant difference between treatment and control, and maybe that's it. I think it's important to note that this is not all produced water. This is produced water from a certain set of fields which have somewhat unique characteristics, and extrapolation beyond this to produce water in general across all fields in California, all fields throughout the United States and the globe, is something that I think probably would be somewhat of an overreach. Those are my comments.
And I just want to add, Dr. Shonkoff and other members of the panel, that part of the task is, as staff goes through and basically drafts the white paper on behalf of the panel, because you're all volunteering for this, the water boards aren't paying you for this. We greatly appreciate the time and effort you put into this, is that I think, we will ask for recommendations because no study answers every question. We can't answer every question. So if there are some of those unanswered questions, certainly we want the panel's input so that the limitations, what maybe you think additional work could be done in the future, perhaps under some type of research process or something, to take some questions a little bit further if need be, if we have questions. And conditions, issues like does this work apply to other oil fields? Is it applicable to other issues as those things go forward? I just want to reiterate to everybody, I think I said this early on, that I think those will be important components of the white paper that we will look to the panel members to add as our summary of the drafts and basically the conclusions, the recommendations, and where do we go from here. Because again, I don't think this was ever intended to answer every possible question that is beyond the scope of this work. And the general question was, is there an issue associated with using produced water over other sources of irrigation water? That was the operative question that I believe the regional board itself was most interested in, and whether there were unintended consequences and potential risks associated with our permitting of this activity. So, thank you. Yes, David.
Hi, Clay. Dave Mazzara, Department of Public Health. Dr. Shonkoff actually brought up an interesting question at his last comment, that this is produced water from a particular area or field, and how does that, or does that not apply when you're looking at other projects that are using produced water for irrigating crops in other areas? But I'm wondering, how does the role of your waste discharge requirements and permitting, does that in some way limit the playing field in terms of what's discharged, so that it's somewhat equivalent across projects and that there's some consistency in what the produced water is being put out?
Well, I think the primary question, and the future questions, and I think it is a question we'll have to struggle with, and maybe as we're drafting the white paper, we'll talk about this a little bit more, because I think Dr. Shonkoff brings up an interesting question, is that it's the economics that drive and the amount of water available in Kern County that drives what water is going to be used. At this particular point in time, it's not economic to take high total dissolved solids produced water, run it through reverse osmosis or some other treatment, and basically make a water suitable for irrigation. However, I don't know what the case will be in the future, depending upon climate changes, the impacts of the Sustainable Groundwater Management Act. We may see changes in what is economic in Kern County, and I would anticipate that if water becomes more valuable, we may at some point see an increase in the types of water that are contemplated for use as irrigation. And one of the things that I was thinking about sitting here listening to the conversation is that You know, as far as the chemical additives, we would have to look at that, but it may not be a whole lot different in the chemical additives for this water versus other types of produced water coming out. That's a question that I think we would need to answer. You know, I think it also depends upon what is the treated effluent coming out of the treatment system look like. Are the metals, because the metals appear to be one of the primary issues of concern, probably not the organic compounds so much. I think there's been a lot of people that we've had through the panel. Dr. Vengash from Duke is, you know, they're doing work that's interested in the inorganics, the metals primarily. Dr. Banuelos, excuse me, I had to remember his name for a moment, but Dr. Banuelos, when we had him come, you know, who is basically an expert on plant uptake of you know, and how that works, said, you know, his concerns were associated with inorganics, not the organic compounds, because we think many of them will break down, they'll volatilize, you know, they'll modify to the point that it's unlikely they would migrate into the soils, get uptaken by the roots, work their way through the plant, and get transferred into the edible fruits, nuts that we're interested in primarily. And so, you know, I mean, I think those are some of the questions that, you know, if we were to analyze the water and if the inorganic concentrations were similar to what we see after treatment now, you know, one of the questions I might want to ask the panel and let you think about till the next meeting is, would that make a difference in our assessment? And you know, if basically the water looks the same at the end of the day, would we expect a difference in what would be uptaken by the plants? Or is there some additional work that you would want to recommend and have that included in the white paper if we see these lesser quality waters being treated and used for irrigation? So that's just what I thought I would add, but I don't think we're ready for that conversation today. And perhaps as we get a little further into the white paper, we get more toward the conclusions and the recommendations, may be the day to have that conversation. And I just also wanted to make sure everybody was aware that Dr. Carl Longley, chairman of the Central Valley Water Board, is here, and I don't know whether Carl has anything that he wants to add.
I'm sorry I'm late, but I was in a CV Salts meeting, trying to make two meetings in one day that are scheduled at the same time.
Can I make a question statement? Is it on? No? Okay. Just helping organize how we're going forward. Just want to clarify, make sure I understood what was said, that everybody is in agreement that we don't need to do what I'm calling the criteria dose analysis, which is the second or third bullet point here. We don't need to go forward with that work, and that we should focus our energies more on filling in the blanks on the part of the projects looking at the breakdown products and some of the other characterization of compounds that are less well known. Is everybody in agreement with that? Because there's a lot of work involved in both those things. Okay. So there's no objections to that.
I think we were saying that to mention the limitations with the breakdown product question, but I'm not sure we were going to wait on our decision for more data on that. Is that correct?
Well, when I was referring to that is, you know, part of what we've been discussing a little bit, you know, with Bernie and I and Rob and the board talking about how to, it's a very wide open question, the breakdown product issue. And so we're looking at the literature and also, you know, what I suggested this week actually was to look at some of these papers that are coming out now that are looking at this problem in the sense that they're looking at whole sample biological type based analysis, such as toxicity assays, because everybody knows there's really no way you can know every breakdown compound product. So it's just a scope of work. We're not, these guys have to finish up. We're trying to figure out exactly how to meet the end game here.
So in my opinion, as I said earlier, to go down the rabbit hole of trying to look at every chemical constituent that's used or in produced water and look at what it's going to break down into under a set of assumptions, which probably will be wrong, just realistically. That's an enormous amount of work. I'm not sure it's going to get the issue that much further along. I think the more simple and efficient way to go about this is to review what's been done on some of these bioanalytical approaches, what's been recommended in, say, a recent science advisory panel report convened by the State Water Board on monitoring strategies for constituents of emerging concern in recycled water, some of their recommendations, because it is a wide open research question. This is, and maybe it's further along than just a research question, but, putting forth, the benefits and challenges of those approaches, I think would be very helpful and would be more time efficient also. So for whatever that's worth.
Just as a response to Seth, I mean, we can refocus that section on breakdown products, looking at those things. Yep. Just to be clear, as part of the literature review, not as part of the crop sampling report.
I thought, just these are completely picky, but I'll forget them if I was going to send them to you. I think in places where I've gone, where you're going, when you talk about the milligrams per kilogram in the crop, and then you talk about intakes, it's helpful if you always use with the crop parts per million, parts per billion, and then milligrams per kilogram in parentheses. And it's something, if you look at WHO, to keep the reader focused on this is concentration and this is intake or exposure. And I know you aren't to that point, but we found that to be cause the least amount of confusion. And I thought your reference to FDA, particularly on the inorganics on the total diet study, is helpful. I think as you write it up, to be able to reference FDA is trying to do this, and this is how many samples they have, and the kind of variability they have is helpful. When you do that, it needs to say U.S. FDA total diet study, because there are about 50 total diet studies in the world, and so you don't want people saying, this is what they found in France and so forth down the line.
Oh, thank you. That's very helpful. That brings us to the end.
Well, let me ask if there are any more questions from panel members. Dr. Clock, are you still with us?
Yes, I'm here.
Okay. You have any questions, Ken?
Not at this point.
Okay, thank you. I'll ask members of the public that if anybody has questions, invite them to the microphone to ask their questions. Looks like Bill Aliud is coming to the
Bill Alio,
microphone.
Environmental Working Group. My question is, there may be a simple answer to this. So you have 347 additives, 180 have published toxicity levels, 65 of those became chemicals of interest. Those are your numbers. So what about the 347 minus 180 that don't have published toxicity levels? So I don't know, I'm not trying to get to a conclusion. I just want to know that other large amount of chemicals, could they end up in the food, or what's going to happen to those? Was there ever a look at them? I think that question's clear.
Okay. So I'm going to take a step back here. Let me use the pointer here. So yeah, there was 347 additives, 90 of which, and then an additional 90 naturally occurring compounds based off of our literature review. When looking at them in total, because there's a bit of overlap, we had 400 total chemicals that we evaluated. In the first step, we sort of identified 107 that had those published toxicity values. We were then able to do some amount of read across, so things like, say, lithium chloride would have the same toxicity as, say, lithium. We basically did that kind of like read across. And then down here, we had developed these ad hoc surrogate toxicity values. So while a number of these chemicals didn't have any published data, we were able to sort of develop a similar value that we could use to sort of compare and evaluate in the same sort of schema as the chemicals with published toxicity values. And so that gave us the total of 180 chemicals. Right? I'm just making sure that we're everywhere. Okay. Now, after evaluating that, those 150 and screening them out for those that sort of had the most acute toxicity, or those that were the most toxic, basically less than 0.5 milligrams per kilo per day, and those that were poorly biodegradable or not inherently biodegradable, or inorganic, sorry, that sort of gave us a priority list to review further in the literature review. And that was part of what we were tasked with, was identifying those chemicals of interest. Now, there's a number of other chemicals that are basically not on the priority list or didn't have toxicity data that we're further evaluating because we don't know much about them. And so we want to understand what might happen to them in the environment. Those where we have sort of incomplete information to make assessments, we need to have sort of a larger discussion about their toxicities, what we understand about them in the environment. And then we have these 5 radionuclides, which are not going to degrade in the environment, are going to likely persist. But what do we know about those levels in California? What do we know about them in irrigation water? And what do we know about their likelihood to be taken up into plants? And so that's sort of where the literature review is focused. I'm not sure that totally answers your question, because the other chemicals that have now been screened out, there are a couple of different places. There are sort of what we refer to as a step 2 here, and these are the chemicals that we know are dietary requirements. They're food additives. They may be used in sort of pharmaceutical goods. In one case, things like bentonite clay is also used as like a laxative. I mean, there are those kinds of chemicals which we're not concerned with as far as their toxicity, because they're used for other purposes. Like a lot of chemicals, they have multiple purposes. Some of them may be in systems where we might have a concern, but they're also potentially used in areas where we eat them. And then we identified 69 of the chemicals which didn't appear to have toxic effects related to chronic oral exposure. I mean, in some cases, if you were to breathe in dust of like silica dust, right? Silica is considered a problem, but then again, silica is also sand. Like there's some of these chemicals which we know are not toxic for a number of reasons, either due to the route of exposure, or because there's animal data suggesting that under very large doses, there's no chronic effect based off of these oral exposures. And that's how these have been all screened out. And that basically all that leaves left after we've done all that, remove those ones, are the ones that are basically on this priority list. We know what we know what the chronic toxic profile is of them, so we understand that part of it. We understand whether or not they're going to degrade in the environment, or at least in water. Thank you. So we know whether or not they're going to degrade in water, and then we basically developed that list of 65 chemicals, which were our priority in the chemicals where we understood the toxicity. But there's still a number of other chemicals which are still being reviewed. Is that
Yeah, I think that's a more clear explanation. I guess when think about, I think it was Dr. Shonkoff said, we have to be aware that we're looking at this neck of the woods of Kern County, this produced water, this area feels it may differ from another part of the county or another part of the world. But I guess to the layperson, they're saying what we're using here is an unusual thing. It's not water from the state water project or federal water project. It is from oil companies, and they're using a bunch of chemicals that we don't know about. So I think that person would go, but are they checking for the ones that are not standard, that we don't expect to see in water coming from groundwater, naturally occurring usually, or pesticide residue or whatever? It is coming from an unusual source. So to me, that's what we want to look for more, or at least as likely as acetone, which apparently is to be naturally occurring on all kinds of fruit. So is there something coming from the upstream source of Chevron or Hathaway or CRC that's different than what we would expect from the state water project or groundwater? And I would say let's make sure we look for those and not say, well, they're, we don't have toxicity data, or you'd have to eat 100 pounds a day of it. So I don't know if there's that other kind of suite of chemicals to look for.
Well, I think this sort of feeds a little bit into what we were talking with Will. I mean, we can only evaluate what we know about and what we have methods to evaluate. And then as part of sort of this issue of breakdown products, I think that's where the remainder of those chemicals where we say don't have a very good understanding, we can at least holistically evaluate them using things like whole cell in vitro assays or other similar methods to look at what are, say, the toxicologic profile on the whole of a water source, as opposed to just these specific constituents where we don't necessarily understand the unique toxicologic properties of them.
And I will add, this Clay Rogers again from the Water Board, that all of our orders, nobody's using produced water without having waste discharge requirements. All of those orders, and I would anticipate all future orders, require the complete disclosure of all chemicals being used. And we have issued orders to manufacturers to disclose even trade secreted information. We've so far been able to negotiate around trade secrets by not getting the exact recipe, but by getting all of the components. So we know all of the components being added. That will be done for future projects if it were to expand. And if new compounds or chemicals pop up, if all of a sudden Agent X gets popped up that has some new chemical that we have not seen before, I think one of the things I'll look for from the board, and one of the things we would expect, is that perhaps there needs to be a little bit of work done on that particular compound if it's something new, to answer these basic questions. So that's part I hope to be answered in the white paper about the conclusions and recommendations. What do we do if something new is used? So I don't think we'll be in a situation where we don't know about something used. And my anticipation is that if it's going to be used, we're going to want to know something about it to make sure that we don't have a problem created. I'll let Will add, Dr. Stringfellow add whatever else he was thinking he should add.
Well, I would going to go say things along the lines of what you said, and also I think that's something that ought to be considered for incorporation in the white paper, about looking forward about how that sort of exact question could be managed. Compounds that we've evaluated, keeping lists of the compounds we know are acceptable, and ones that when something new, so that there's a mechanism, so if something new comes in, it's flagged, and then we can either discuss it. And I think what that eventually evolves to is what we talked about early on, which is this idea of an approved list. And the idea that you might, what they're doing up in the OSPAR in the North Sea, where you just have things that you're allowed to use, that it's known you can use those, and if you want to use something else, you have to go through a process. I think that eventually is sort of a logical outcome of that kind of approach.
Thank you, Bill. Anybody else have any comments or questions in the room? Do we have anything by email?
Yes, we do. We have a couple of questions from Justin Bass, and they're for GSI. There's a number of questions here. I don't know if it's best for you if I read them all at once, or would you like me to go through them one by one? Okay,
Let's go one by one, just so it's a little easier.
you got it. Okay, so the first question is, does GSI know the full list of chemicals used by the oil companies during maintenance, well stimulation, and oil drilling or fossil fuel extraction?
It's our understanding that the 347 chemicals that we were provided with represent all those that are being used during production, and that includes maintenance, extraction, development. Is that correct?
That is correct. I'll just add that we have that complete list. I also want to add the fact that, to our knowledge, and I believe we have confirmed this, there are no hydraulic fracturing activities occurring within the fields or have occurred within the fields where produced water is being recycled for irrigation. So the well stimulation, but even under that, all those chemicals are required to be reported if you did well stimulation under Senate Bill 4 that was adopted a couple of years ago. And I believe all of those chemicals have to be reported to Frac Focus.
Okay.
A different database, Dr. Shankoff, thank you. Yeah, that's not an issue we deal with because these particular oil fields are not amenable to hydraulic fracturing, and it has not occurred because they're not, it's in a porous media, not in a rock that needs to be fractured in order to increase the permeability.
Okay. Second question is, what are the knowledge gaps?
In what context?
That's all he. Yeah.
Within the literature review and within if you were, Mr. Bass, if you were actually following along here and can see my screen and the screen we're presenting. So within the scope of the literature review that we're presenting, we are going to identify those places within the context of the chemicals that we are evaluating and within the uses of water that we are evaluating with which we don't have sufficient information to determine whether or not the crops or the use of produced water to irrigate crops poses a health hazard. So that's the basic scheme of how we're evaluating whether or not we have knowledge gaps.
Okay. And question number 3, does GSI know where the oil companies get their water?
When? I mean, all the irrigation water data is available on the Water Board website, and so that represents all basically measurements of and locations from where that irrigation water is being provided.
And let me add something to that, in that, we do not know the source of all the waters that are being used within the fields from the oil companies. I think Mr. Bass has asked that question in the past about how to do that. That is more of a question under the jurisdiction of the Division of Oil, Gas, and Geothermal Resources. So we don't know the source of all of the water. We certainly have extensive testing of the water that's used for irrigation. We have a reporting of the chemicals that are being added that are included in the analytical analyses, along with general minerals and other, a fairly comprehensive list of analyses that are being completed, but we do not know what the source of the water is that the operators are, if they're importing water from other sources. And I think a significant amount of the water is water that's recycled within the, most produced water is actually recycled for use within the oil companies itself, particularly for their enhanced oil recovery efforts.
Okay, next question. Did GSI pick the test fruit? If not, who picked the test fruit? And where are you getting control samples?
I'll answer that question, and Mr. Ansolba here from Coelho Water District is here also, and if he feels a need to add something, I'm sure he won't hesitate to jump in. The fruit samples were picked by a third party hired by the Coelho Water District, observed by the Regional Water Quality Control Board staff, because we went out in the field when the fruits were being collected, fruits, nuts, and different crops. I believe we were present at all of the sampling that was done. The samples were collected, they were transferred to our staff, and our staff arranged for the shipping to the analytical laboratories. So that answers about how it was sampled. Coelho staff nor Water Board staff directly picked it, but Coelho representatives, Water Board representatives were present. We observed. We have field notes. So that answers the portion about who picked the samples. What was the second part of that, Rebecca?
Where did you get control samples from?
Control samples came from fields known to have not been irrigated with produced water. So they were irrigated either with available surface water, groundwater, the normal agricultural water supplies being used within the southern San Joaquin Valley that had similar types of cropping cultural practices, I guess is probably the right way to put it, to try and minimize the variability from the same general area as close as we could be, but to make sure we were outside areas where produced water had ever been used for irrigation. So that's where the control samples came from. Hopefully that, Dale, you want to add something?
Maybe. Oh, there we go. I just want to add that there was one round of early citrus sampling where Water Board staff went out with staff with Dr. Stringfellow and some folks from University of Pacific, and we actually conducted that round of sampling and transportation to the lab.
Okay, so one set of samples was picked by our staff, and the remainder of the samples were picked by the third party. Thank you for clarifying that.
Okay, next question. Did you eat the apples? Did you eat the carrots? Do you eat the food crops you test for toxins? We are talking about food after all.
I mean, if this is a question for me in particular, I eat produce from California, unaware of where its water sources are. Now, those crop samples, I believe no one ate any of them during the sampling. They were just placed in jars and then tagged and shipped off to the laboratory. But I don't know if anyone else who's been on any of the sampling trips has eaten any of those crops.
That's not typically part of the sampling protocol.
No, that's, and Mr. Bass, I just want to add that it's not appropriate for our staff to pick somebody else's crop and take it home to consume. That's their product. That's not what we do. I will tell you, and as the Assistant Executive Officer of the Central Valley Water Board, that I too eat fruits, nuts, and vegetables grown in California. And this effort has not caused me to look at the labels of who produces it or who grows it in an effort to make sure that I do not eat crops grown with produced water. So, and I think all the work that has been done to date has shown that there's no difference whether it's grown with produced water or normal irrigation water. We don't see a difference in these compounds. So I personally see no reason to avoid those particular crops.
This is David Unsullivan here, General Manager of Coelho Water District. And most times when either myself or my staff was out observing the crop sampling, if it's anywhere in the mandarins, oranges, not really the almonds or pistachios because they were still a little green, but we always sampled the fruit and ate parts of them. And when they sampled the apples, we did the same then. But all of our staff at the water districts, anytime there's crops grown out in our districts at time of harvest, usually we always sample them. The farmers will actually bring them in right out of the fields. So we've eaten all the crops that are grown within our district for the last 25 to 26 years. So I haven't lost any weight yet.
Okay. Did GSI do the lab work? If not, who did the lab work?
The laboratory analytic work was done by WEC Laboratories in Los Angeles County. I believe it's either is it City of Industry or La Puente, however you just want to identify it. And then the other was Apple Labs, which is in Clovis? In Clovis. And we received.
And I'll just add that Apple is APPL because it's an acronym for Agricultural Priority Pollutants Laboratory, currently in Clovis, California. Used to be in Fresno, but they changed locations a few years ago and moved to a suburb of Fresno.
Next question. You said chromium. Did you detect chromium-6? In which food crop did you detect chromium or chromium-6? From whom did you get the food crop?
There was no indication of which valence of chromium it was.
It's total chromium.
It's because it's total chromium. Let's give me a second here. Okay, chromium was detected in treated and control samples of carrots, and I believe that was at trace levels.
Okay. Next question. You said methylene chloride. In which food crops did you detect methylene chloride? From whom did you get the food crop?
Methylene chloride was detected in carrots in both control and treated. And let's see, move that across. In control pistachios.
Next question. You said MTBE. In which food crop did you detect MTBE? From whom did you get the food crop?
MTBE was detected in the most recent samples of pistachios in both treated and controls at nearly exactly the same levels. But
Hi, this is Will Stringfellow, Science Advisor. I just want to point out on the methylene chloride, there's no reported use of it on oil fields, and as far as we know, it's not used on agricultural fields for any purpose either. It's really commonly used in laboratories for solvent extraction procedures as part of the analytical concentration of the samples for analysis. It is a few hits of methylene chloride here and there are, in my experience over the years, you see them come up sort of randomly sometimes in analytical results. So when we look, if it's not something that's recurring over and over again, we looked at it with a little skepticism as to whether it's a particularly significant result. And then also on the MTBE results, where those are still under review, I'm personally skeptical that it's actually MTBE. It's a very small molecule and can be confused with other molecules, so we're reviewing that data. I wouldn't go to the bank that that's actually MTBE in those samples.
Thank you.
Thank you.
Okay, next question. Who pays the bills for GSI's services? Does GSI have any affiliation with oil companies?
Let me answer that question, because that goes back to the memorandum of understanding between the water users and the Central Valley Water Board. The operators that are using the water for irrigation are paying GSI's bill, but technically they report to the Central Valley Water Board and to me as the manager of this project. Coelho Water District and the other irrigation districts have no control over the technical aspects of the job. There are no technical conversations between GSI and the water users without going through me. Now, administratively, the payment of invoices, dealing with things like if there's a change order or something like that, that has to be approved by Mr. Ansolbeher as their project manager. But the technical work, the work that is done and the technical decisions are made with input from the water board staff and do not include input from Coelho Water District. So I just want to be clear that we felt it was appropriate for the users of the water to pay the bills, not the citizens of the state of California to pay those bills. But we would maintain technical control over the projects to make sure that we could have a technical integrity that was beyond question for this work.
Okay. And then the last question is for Mr. Rogers. Does the Central Valley Water Board have rainwater recapture? Do the farms in Kern County have underground aquifers that they can use to capture the majority of rainwater? Maybe we don't need to expand oil field wastewater farming in California. Maybe we can focus on sustainable farms and expand rainwater recapture infrastructure. Also, maybe we can stop the oil companies from using any water. Maybe we can give that water to farmers instead.
First, let me answer the question regarding groundwater recharge, which I assume is what we're talking about when we say rainwater capture. Certainly all over the Central Valley, there are significant strides being made to recharge groundwater with any type of excess surface water during times of periods where we have high flow. In order to put as much water in the ground to store it for future use as we can. And those activities have increased significantly in the recent past, including within Kern County. Coelho Water District itself and the North Kern Water District have significant recharge basins where they take excess surface water flows, particularly during high flow years, and put them out in surface ponds where they percolate and recharge groundwater. So that's the case. As far as the appropriateness of using water sources for oil activities or giving that water to the farmers, those certainly are questions that are beyond the jurisdiction of the Central Valley Water Board. I can't answer those or even offer an opinion. Those are really political issues that are answered at a different issue. Than it's not a technical issue, it's a policy issue. That's something that's above, my pay grade and outside the intent of this particular effort. So, unfortunately, I'm not going to personally weigh in on the appropriateness of that use one way or the other.
That's it.
So we have no other questions over the internet? Okay. Mr. Bass has not asked any follow-on. All right. With that, I'll open it up again for any questions from the panel members or general members, just to make sure that we don't have anybody out there with a question or something they would like to add. It is.
We've got an update on the white paper as well. So
Well, I guess I should back up a little bit. I'm getting ahead of myself, Bill, again. Josh, why don't you give us an update on the white paper, since ultimately that's the most important thing here.
I'm gonna do this update at my station because part of it's gonna be getting feedback from the panel, so I can take notes. So
One thing in the moment, I see the time is 12:15. How long do you think this is going to take, Josh?
my part's only about 6 minutes, although I do have some questions for the panel that we'll have kind of a little discussion. There's 3 items, one of them we've already kind of talked about, so
15, 20 minutes?
probably something like that.
Okay. My thought is that probably instead of breaking for lunch, everybody's probably interested in just moving forward, getting done, and adjourning the meeting.
Okay. So this presentation is to give an update on the white paper and let people know where we're at with that. So the purpose of the white paper is to present the results and the findings of the food safety project. As of now, Water Board staff has completed 3 versions of the white paper that have been distributed to the panel for comments and the public for review. The first version is an outline, and it's dated 28 June 2017. The second version was presented during the last public food safety meeting in August. And the most recent version is dated 12 November 2019, and that's the version that will be discussed in this presentation here. Significant additions and updates for this white paper were made to the following sections. These sections include treatment of produced water, oil-filled additives, quality of produced water, and the summary for the Task 1 report. Before the white paper was distributed to the public for review, staff sent the white paper to the panel for review and comments. Feedback included editorial changes, clarification on specific items of the paper itself, and 3 general comments that were received by the panel members. Due to the nature of these comments, they were not able to be implemented in the most recent version, which is why we're giving this update and wanted to talk about these with the panel members and kind of get additional feedback regarding those questions. So the upcoming slides will talk about those questions specifically. So comment number 1 that was received is says that Category 1 chemicals that are called essentially non-toxic, it would be better to say of low concern for toxic effects at concentrations normally encountered by humans and at concentrations expected in irrigated crops. The question for the panel from the Water Board or from Water Board staff is that should the description for Category 1 chemicals in the Task 1 report and the draft white paper be changed? Right now, it's currently says essentially non-toxic. Do we want to change that definition to of low concern for toxic effects?
And I think this comment was brought up by Dr. Clock in his written responses, and I think the idea that we had, if you'd had a chance to look at those in the last couple days, is if you guys could kick it around, or if you had any significant preferences as a panel. If you feel put on the spot, we can also take your written comments on that matter and work up another draft of the white paper based on what the general consensus is.
Okay. So, well, we'll look for some written comments. We'll send out an email and see if there's any written comments back from that. We'll probably have a deadline of 2 weeks or so, and we'll look for your feedback then. The second comment that I just wanted to present here during this meeting is it states that chemicals designated as inherently biodegradable should be retained on the chemical of interest list. According to Will Stringfellow's memo attached to the Task 1 report, it cannot be assumed that inherently biodegradable chemicals will rapidly biodegrade in all environments or conditions. Further study of the fate and transport of these chemicals would be reasonable next step. So the question from the panel, like Dale said, we'll be sending these out in an email as well, so if you want to provide written comments. So should the chemicals of interest list include inherently biodegradable chemicals? Right now, the chemical of interest list focuses primarily on poorly biodegradable chemicals. It does not consider readily and inherently biodegradable. Yes.
Please do.
So there's standardized testing. We talked, I think, about that at the last meeting some, and there's the readily biodegradable and the inherently biodegradable, which show that the compound does biodegrade on some conditions. And I may have poorly worded part of it, but we included inherently biodegradable because we're trying to prioritize, saying we've got a long list of chemicals. What do we want to most focus on? And we're most focused on the things we know least about. And then there's another category of chemicals that have been tested and failed the test. But typically they fail the ready biodegradability test, which is a very specific test that it's well known not all compounds that biodegrade in soils, for example, like an agricultural soil, would break down in that test. So part of the triage to focus energies was to say compounds that had passed these standard tests, which include the ready biodegradable and the inherent biodegradability test, that those were considered low probability of persisting in agricultural soils, and that these other ones that either had not been tested or had failed the ready biodegradability test were more worthy of including on this high priority list. I'm not sure that clarified it for everybody, but I think people should make a decision, but depending partly on how, what we think are the critical things we need to look at, but things that are inherently biodegradable are likely to biodegrade in aerobic agricultural soils. It would not be what I would consider a high priority thing of concern at this point. I would start putting it on the list of things that are probably not going to persist very long in the environment. So the question is, do we want to go and, start including those in this list of the 60, I think it is, compounds at this point? 65, that would expand the list of 65.
To how many, Will?
This is Ken from OEHA. I was the one who made that comment. Well, one of the things I was thinking was that even though these compounds might be, the inherently biodegradable compounds might be expected to biodegrade readily in aerobic soils, the question would be is what is the rate of decomposition, and is that a rate which is quick enough such that a plant wouldn't have a chance to engage in quite a bit of uptake prior to biodegradation. So that was my only concern.
And I think that's a good comment. And there are, trying to make sure I don't misspeak here. There is guidance from the US EPA, I believe it is, on how to interpret these tests in terms of certain kinds of assumptions about decay rates. And I started to look at that literature. I'm not prepared to discuss it exactly, but maybe as part of the literature review, we can look into that and see whether, and work with Dr. Clock on deciding whether this is appropriate or not with the panel. But there is guidelines in the activated sludge modeling, that EPA activated sludge models, there is guidance that says if the compound passed a ready biodegradability test, then you can assume this rate of decay. If it passed an inherent biodegradability, you have to use a different rate of decay. So we can look into that. But there is an acceptance that there is going to be a rate of decay. So why don't we pursue that more and work on it?
That sounds good to me.
All right. Looking at comment 3, this one says that the assumption that all of the chemicals used in oil and gas development activities will stay those chemicals by the time the produced water is being tested is at best a significant reach. Many or most of these compounds will interact with other compounds, degrade to daughter products, and otherwise transform. As such, while chemical disclosures is critical to the development of risk-relevant science, it is inadequate to build a reliable monitoring program to manage those potential risks. Now, I know we talked about this before, earlier in this presentation, or the previous presentation, and we had come up with that basically the discussion of daughter products would be talked about in the Tax 2 literature review, where we do a review of bioanalytical results and see if there's any other recommendations available online that we can kind of reference. Is there any additional feedback or comments for that? Does that seem appropriate?
Well, in the spirit of transparency, I submitted this comment, and that sounds fine. I think it's relevant and transparent to communicate that while disclosure of chemicals and all of that is a central pillar of being able to assess this activity from a scientific perspective, it's not the only central pillar. And so discussion of gaps and what those other pillars might be, I think is appropriate.
Thank you. So excluding the comments that were talked about in this presentation, most of the comments that we received from the panel were incorporated into the most recent version of the white paper, which was sent out to the public through the Food Safety Lyris list on 12 November 2019. This white paper will also be available online shortly. It is with our IT department and is being posted to the food safety website. So that'll be hopefully up in the next couple days. For the next steps for the white paper, we'll be presenting again at the next food safety meeting. And what we're working on right now is kind of in progress is the Task 2 summary, the Task 3 summary, a discussion of data gaps and recommendations by the panel. So those are currently being worked on, and we'll see more of that available in the next version of the white paper. So that kind of concludes the update of the white paper. Are there any comments or feedback from the panel?
Yeah, this is Dave Mazzaro, Department of Public Health. Can you just remind us again the timelines for the white paper, the draft for us to look at, and what your ultimate timeline would be to have that in some final form, at least draft-wise?
Yeah, we sent the previous one out a couple weeks ago, and so we've got your comments back from that. We've gone through them. We have them identified. Right now, as GSI is working on the Task 2 and Task 3 report, as we get those copies available, we'll be doing a summary and incorporating that into the white paper. So it's kind of, it's kind of dependent on the other task reports going forward.
And I'll just add, Dr. Mazzara that my intent is to have a draft white paper to the panel by the end of the calendar year. That's my goal. I'm not sure we're going to be able to make it. But that's my goal, because what I would like to do then is probably provide about 30 days for the panel to comment on it. Have us be able to take those, incorporate your comments, put a draft out for public review, have the next public meeting actually on the white paper, and then basically get the panel's blessing as we work through removing this, so that I can take that white paper to our board, basically for acceptance by the board. And basically then, that would complete this, and have a public discussion about the white paper with the board members. So I would really like, as I mentioned early in the meeting, I would really like for that to happen in April. What was it, April 15th, 16th, something like that, 18th, 19th?
16th and 17th.
16th, 17th, I was close. But mid-April is when that board meeting is in Bakersfield, because this is an oil field issue, and so it'd be great to be able to do this in the area where this is an issue and people live that interact with these activities. If not, then it will be in June in this room. But that's my anticipation, is that by June at the latest, we will have completed that, and I'm going to try and make that happen in April if there's any way I can push everybody to do that.
So
Yes, Barbara.
I would encourage us to get it done by April, mainly because crops start being grown, and you don't want to throw decisions out there in the middle of a crop year if you can help it.
No, I agree. I would really like to complete this in April, but at the other token, the one thing I want to make sure is that we get this right and we put the time into it that it deserves. I don't want to put something out there and complete something that's not as good as it would have been if we had done just a little bit more thinking about it and putting the effort into it. So I want it done fast, but it has to meet the standard that is acceptable to the panel and the water board at the end of the day.
So to clarify, you're planning on being the evil Santa Claus who's going to give us this report around holiday time?
I got no problem giving it to you, Will, on Christmas Eve and asking for a review by the day after.
That was a little bit too religion specific. But.
During the holiday season.
Well, so as far as that goes, I guess with the issues that we brought up today, we'd be looking for something back in a couple weeks. And then I think Josh is pretty much done, so now might be time for Mr. Alude's question.
I think we are actually to agenda item number 7 now. Even though I've tried to move this along quickly, but I can't skip things either, so.
Be pretty brief. I know we're going to do this before a lunch break, not have a lunch break. One was on soil sampling, and that still seems to be a missing link in this, that the logical thing would be to take profiles across several farm properties, control down to, from 6 inches down to several feet, especially where this water's been used for about 2 decades plus now. I don't know why that hasn't been done. Maybe the Duke study's looking at it. I appreciate if that does get done soon. And I know the first focus on the citrus is ripening. We got to get this out. I would have gone right for the soil and then said, okay, now the citrus, the pistachios, the almonds, and the root crops. But let's get a soil profile and see if there's anything building up. A concern would be with farm workers when dust. You all see what happens in the Central Valley or any farm area when it's dusty. People breathe that stuff in. So that's one thing. And then sort of related was when Dr. Banuelos was here, I asked him about growing food in that soil. He said, I would not grow tubers or root crops in that soil. Period. That's what he said. I know he's not a member of the panel, but I'd like to see that addressed in the white paper, whether you recontact him or he is the really only expert, and I appreciate the expertise on this panel from various disciplines and agencies, but that's what he said right here while I stood here and he was at that mic. So let's deal with that, what he said. Why did he say it? Do we need to be concerned, even though thankfully so far control and real samples are showing about equalness in terms of the various contaminants and constituents. Lastly, I just want to say, I think I mentioned this before, that US EPA came to me, I think to you too, and nationally they're looking at the further use of produced water in the United States, including for irrigation. So I just want to state our appreciation for the food safety panel, that the volunteer time that members have given, the staff time devoted to this, and to the water district's cooperation, because people are looking to you. I think this is the first effort at this nationally. So it's really important work that you're doing. We look forward to the eventual white paper conclusions and put this to bed once and for all. Thanks a lot.
We appreciate your comments, Bill. I will add that, I think the issue of soil sampling is something that will be discussed within the white paper. Again, in the interest of time, we felt right now the primary thing was, is there a problem with consumption of the crops? And based upon the sampling that we've seen, it appears the answer to that is no. It's also bolstered by the fact that we believe we are also sampling I believe it's a 40-acre parcel of oranges that is the longest used, or the parcel that has been irrigated with produced water for the longest period of time. Because we wanted to include that parcel, just because that would be the one where if we're going to see a buildup, the longest usage would be the logical point where we would have the greatest buildup. But I think the soil questions are a thing. I agree. I mean, Dr. Longley and I personally both tried to get Dr. Banuelos to be on the panel. I tried to lobby him pretty hard because he works for USDA at the research station down in the Fresno area, teaches classes at Fresno State where Dr. Longley was the dean of the engineering department, or I guess the chair anyway. I guess he wasn't the dean. Oh, he was the dean, excuse me. I shouldn't minimize, should not minimize that. But anyway, we did attempt to do that, and I think, certainly I will, and Dr. Longley probably also will contact Dr. Banuelos and see if nothing else, if we can get him to comment on the white paper. If he'll take a read and provide us comments that we can consider. But I appreciate your comments, and I remember that statement by Dr. Banuelos also. So it is not unheard, but I think the important thing is that we don't see the difference between the control and the treated to any significant effect. Anybody else have any questions, comments? Any other questions on? All right. Josh, do you want to talk about the action items, agenda item number 8?
Yeah, so we've got 3 action items. The first one is to send the presentations that were gone over today out through the food safety LIRIS list. The second one is that the comments that we had today that were talked about in the white paper update, we're going to basically on our discussion today kind of put together how the water board wants to address those 3 comments, send it out to the panel, and get your recommendations from that to see if you concur with our approach to those 3 comments. And then the third action item is to reach out to Dr. Banuelos about getting comments regarding the white paper.
All right.
We got,
So,
oh, sorry, one more question just came in.
oh, okay.
This question is from Justin Bass. He asks, how many water districts now use oil field wastewater? Can you read them, please? Will the Central Valley Water Board expand the use of oil field wastewater to more water districts? If so, how many other water districts are interested in oil field wastewater? Can you list them, please? What is the price of oil field wastewater? What is the price of other agricultural water? Would the oil companies incur a cost for disposal of oil field wastewater if they didn't sell their wastewater to the farmers? Where do the oil companies dispose of their oil field wastewater when they don't sell it to farmers? Are they using underground injection for disposal?
Can we take those questions one at a time? I'm afraid I'm not capable of. So I'll let you start, and I'll do my best to answer, and if anybody else wants to add.
Okay, I'm
But
sorry.
I'll try to go through this relatively quickly.
Okay, let me ask the first question. How many water districts now use oil field wastewater? Can you read them, please?
3.
Do you,
Coelho Water District, North Kern,
North Kern Water Storage District.
Okay.
Kern Tulare Water District. And we have Sherwood Hills LLC and Jasmine Ranchos Mutual Water Company. And those are all listed in the white paper that was sent out through the LIRIS list.
Will the Central Valley Water Board expand the use of oil field wastewater to more districts? If so, how many other water districts are interested in oil field wastewater, and can you list them?
Well, the Central Valley Water Board will not expand it. That will be dependent upon folks that come to us with proposals to use the water and the demonstration that it's an appropriate use and that it doesn't impact the beneficial uses of groundwater through waste discharge requirements. Who's proposing to do that? You know, there would be speculation for the most part on my part, and I'm not going to do that except to say that I hear rumors of general interest, but I don't think we're currently holding any reports of waste discharge with a specific proposed project. Next.
What is the price of oil field wastewater? What is the price of other agricultural water? Would the oil companies incur a cost for disposal of oil field wastewater if they didn't sell their wastewater to farmers? Where do oil companies dispose of their oil field wastewater when they don't sell it to farmers? Are they using underground injection for disposal?
I actually think some of those numbers may be in the California Council of Science and Technology reports that come out. I do not have personal knowledge about, you know, water values vary. I don't personally have the knowledge. Would the oil companies incur a cost if they had to dispose of it? Yes. But exactly what that would be, I'm not the expert in exactly what the economic burden of that would be.
Just to follow up on that question, he asked, where do the oil companies dispose of their oil field wastewater when they don't sell it to farmers? Are they using underground injection?
Yes.
And that's it for now.
This is Seth Shonkoff from PSC and UC Berkeley. I will also say that answers to a lot of these questions are in a report which was conducted with the California Council on Science Technology and hopefully will be released soon.
So with that, that brings us to the end of the meeting. And unless there's any other comments or questions, we'll adjourn the meeting. We have not set the date yet, but my hope would be is that, well, if we have any hope of meeting an April board meeting, probably sometime around mid-February, we would need to have the public meeting to discuss the white paper. So with that, I want to thank everybody for their participation and their questions, and have a safe trip home. Thank you.